Hello, you developers. My name is Henrique Bucher. What I want to do today is test and show how virtual function calls in C++ are translated into assembly language. How GCC implements the virtual table and the optimizations that GCC slash G++ realize deploy when to make the virtual function calls faster. So what I want to do is here I have an empty folder. I have Ubuntu with G++ 4.8.2, and let's see what G++ does with um, one example that I'm about to put in to write. I don't have anything right now, so I'm gonna start writing as I go. What I want to do first is create one C++ file with a main function, and put a couple of classes in there, one base, one derived classes, and instantiate them in real time in the main function and see how G++ optimizes it. Then afterwards, I want to create a shared library with these two classes inside. Then I'm gonna create the main function and instantiate these classes, and I should expect that the shared library will prevent G++ to make the same optimizations. So let's create the first file. I use Emacs to compute that. This is my main function. So what I want to do is let's create the classes. I usually include stdint that has all the integer types. So let's have a class, let's call it base for the lack of a better name. Base will have one constructor, one virtual destructor, and one virtual function call. This virtual function call, let's call it ID, and let's make it return 1. It returns a unsigned int32 and contains no members, member variables. The class derived is a base, public, and what we can do is let's make it return a different ID, return 2. Okay, and then in main, what I want to do is I want to have a pointer, but I want to create a derived class. Then I cache this value is the ID. Delete the object and return the ID to the to the console. And this is pretty much it. That should make it. Let's try to compile. Main cpp o main, and it does. We have an executable called main. It does execute. We don't see anything because the return value is not displayed, but with the dollar question mark we can display the result, which is 2, is what we expect, despite the fact that we are calling obj, which is appointed to the base class. We get the value 2, which is indicates that this function in the derived class was the one called, which is what we expect this happen. Now, what we want to see is how this code is translated into assembly language. To do that, instead of compiling this into a binary, we're going to use a little flag that's not very well known. This -s, what it does, it will compile everything the same way, but will stop short of assembling the binary. So the result, the final result of G++ when this -s, capital S is used, is the actual assembly text file. So that's why I placed the .s, which is an indication for assembly code. Alright, so now we can look at main.s. Alright, so again, let's open it side by side, just to see what we have. The main cpp. So here we create the derived class. Let's see where the main function is. Alright, so we found the symbol. Type is main function, and we are gonna see now that this is stack manipulation. It saves the stack, then stack again. Alright, so this is the code that matters. It's moving into EDI. EDI, as you should know, in assembly x86 64, the first integer parameter has to be passed in the RDI or EDI, in the D register, DI register. In this case, we are calling the new operator with passing parameter 8, which is the size of the object. If you don't know what this garbled or mangled name means, you can basically go to the console and call C++ field and pass that name. You're gonna see that this is the operator new. Alright, so again we let's go to main, and here, as we saw, this is the operator new. After we call the operator new, it returns in the A, and it's R because it's a 64-bit A register. So it returns in RAX the pointer that to the memory that was created using the operator new. So we store the pointer A this pointer in the register B, and we store move from B to D as well. This is the actual constructor. So if we do it again, we copy that name and we pass to C++ field. We can see that this is the this default constructor. And where is the main? Okay, this is the default constructor. Here is doing a bunch of other things, adding, and but what's interesting really is here. You remember that A contained what it's doing here is computing the pointer to the function, to the virtual function. So this is actually this star here means that this is a virtual function call. So it's calling the address that's pointed by the RAX register. This is actually the ID call. The next one, this is the actual destructor, which is also a virtual function call. So you see that there's not much any optimization done, and the reason is because we didn't compile this file using any optimization. This optimization is 0. If we give this, if we place the optimization flag, let's see what happens now. Now, main S. Now, it's likely. I like in the console. So now it's we are gonna see something more different, and actually much more much simpler. This is the entire main function call, the entire main routine is just a few assembly instructions. This is doing the same. This is the part. It stores 8 in the DI register and calls new. Returns in RAX the pointer to this object. Now, what it's doing here, it's moving the value of this symbol that's located in the program into the address pointed by RAX, which means in the pointer to the object, the first 8 bytes contain the virtual the table, the virtual table for the derived class. So this is basically giving a type to the memory that we just allocated. So this is allocated in memory 8 bytes, and this is giving it a type. Now the pointer to this object is now moved into RDI. Again, the DI register is the first integer argument, has to be the first integer argument to any function call, that provided that the function call has an integer. In fact, every C++, every method that's called in an object, the first argument is the this pointer. So this makes sense. We get the pointer to the object and store in the DI register. Then we call the this is the first destructor. Why do I say first destructor? In C++, um, every class has two destructors. One destructor is what we call the delete destructor, and the other is the normal destructor. The reason for that is we might even be able to see it here if we search for it. Yeah. Okay. Yeah. One destructor, as you might see here, this is the destructor that the delete destructor. You see that is calling the delete, and then calling the actual destructor. Um, so what happens is, if you go to main, where is that? So this is calling the destructor on this pointer that we created, and after the object is destroyed, we move the value 2 into the A register, and the A register is what's returned to bash to the environment through this through the when the function returns from here. So the compiler figured out that in compile time that the result of this virtual function call was 2, exactly because let me open the main CBP. So it knows that the result of this, even it this being a virtual function call, is 2, because it has all the information it needs to figure this out. So that's why it doesn't even call the ID. The ID virtual function call just disappears. So the compiler was able to optimize away these functions. They just don't exist. It's a very nice job the compiler did. It basically didn't make any call. It just computed everything in real at compile time, saving us a lot of time. So if you have an argument against using the virtual function calls and using templates or the patterns or the mechanisms to communicate between um, two classes, two objects, the cost of virtual function calls should not be one of them. Should not be taken in account, because virtual function calls, first, they are done in a very smart way. They most of the time the compiler can figure out that what classes are concrete classes are going to be called. So there is no table lookup, and there are many optimizations that the compiler does, like not recomputing this the virtual the not recompute the address of the function every time it gets called. It just caches and reuses even for different objects of the same class. So let's make this more difficult now. Um, what I want to do now is I'm gonna create another main function. So let's copy this one and let's do main lib cpp. Now let's make a copy of main. I'll just double copy the same cpp file and create libtest cpp, and let's edit this file. Actually, let me copy it again. Then it's just a matter of it's just going to be a matter of deleting code. Alright, so let's go and make the header first. So in the header, I'll just remove everything that is implementation. Leave the classes just naked, and the main function does not belong here. So this is the libtest.age. Let's go to libtest.cpp. This one I want to include the libtest.age, and this goes away. What we want to be here basically are just the implementations of the base class and derived as well. Derived. Hopefully this is not gonna take much time. Derived const, and this does not belong here. This is just a library. Alright, so now let's edit the main function. I'm going to include the libtest. The classes go away, and that's it. Now this should compile, hopefully. So let's do g++03 main lib.cpp dash let's compile the libtest cpp-o libtest.so. Now I need the fpig to create relocatable code, and I need also the shared to tell the compiler to create a shared library. That should be it. I have an error. Libtest cpp 6 cpp. Yep, this doesn't belong here. Let's compile again. Compile. It created my shared library. Now I wanna just compile my main function, and I'll just -o. It's gonna be called main lib. Of course, I don't have those. I have to link against the library test, and I have to pass the current folder as well. Alright, so now it compiles. Let's try to run. It should result in 2. That's what we need. So this, even if you do an strace, we can see that it's actually opening the oh, strace has a problem with the buffer. Never mind. So let's look now at what the compiler did. Instead of compiling like this, let's compile with our known -s flag. Let's move this to the assembly extension, and let's see what the compiler was able to do for us. Main lib.s. let's okay, right here. So this is the function. We have debug. This is the definition of the function. There's a global symbol. Um, stack. Alright, so this is where we begin. Alright, so moved number of bytes into di, and we call the operator new. Remember this is the mangled name for the operator new. Then the resulting pointer is stored in the di and bx registers, and the AX register is passed to as an argument to this is the constructor of the base class. So let's make sure that this is the case. We can do this again. We can just call C++ filter on it. Yes, that's the constructor of the base class. So far, alright, so far, again, now once we return this, so we call the constructor on the pointer for the memory that was returned. Now the pointer is in the bx register. We move into the di, because di has to be the first argument, like pretty much like this. We copy the ax into it. So this is the pointer to the memory that we replaced in di, and we call here this is the virtual function, the virtual table address, and we are storing it in as the first bytes of the object that we just created. So the first, what this tells me is that G++, for every object that's created, it stores the address of the virtual function table as the first bytes of the object with it. Alright, so then here is where things get interesting. So here we should have a virtual function call. If you remember, in the previous case that we had, this is the original file. To the right is the original file that we have, this monolithic C++ file we compiled with -03, and we can see that we had, where is that? Oh, we can see that we had quite a few oh no, this is the second one. This is the optimized, so it really optimized everything. But in this case, with the shared library, it's surprising that the compiler called the function ID again. This is let's pass C++ field on this name just to be sure. So this is the derived ID. This is the address of the ID function in the derived class. Therefore, the compiler is not doing any a virtual function call here. It's not taking address of anything. It's just calling directly the ID method in the derived class, passing the pointer to the object as an argument. So there is no overhead for this virtual function call here, because the compiler, even using the implementation of the object being in a shared library, the compiler was still able to figure out that this object was a derived object, not the base, and just resolve the virtual function mechanism at compile time. So coming back to the original argument, if you are scared scared of the performance costs of virtual function calls, and you're not using it because you think that this might be a bad architectural decision, what I can tell you is that these virtual function calls, they are the compiler makes they are very fast, because the compiler makes sure that whenever it can figure out which objects are gonna be called, for sure it does not use the virtual table at all. So there is no um, cache L3, L2 cache trash because of the virtual function table lookup. And most of the time that's what happens, is just it becomes just virtual function calls. It becomes just normal function calls, not virtual. And if by any reason, if this function was had a means to be inlined, the compiler would inline it. The rest of the code is, this is actually one function call. This is the destructor call. There are reasons why it is done this way, but this is the only function, virtual function call that's made in this file. Then here we have the stack and return. So the idea, the purpose of this video was to show that compilers have made a long way to optimize and to diminish the impact of virtual inheritance and virtual inheritance, virtual function calls, virtual methods in C++, to the point that I would certainly recommend using this as everywhere that you can. There is no overhead, and the flexibility that one gain by having by using the virtual methods is just it's just overwhelmingly more than any performance impact that it could possibly be.